Okay, hi guys. So we'll be continuing on seeing more on thermodynamics of reversible reactions. So in the last lecture, we saw a term which is called delta Rg naught, and we saw it is equals to minus RT ln K equivalent at equivalent point. So delta Rg naught is a measure of equilibrium constant. Okay, and if delta Rg naught is positive, then K equivalent is less than 1, which means that we have a less conversion of reactants into products. So if delta Rg naught is positive, then K equivalent is less than 1. This means less conversion of reactants into products. Okay, and then we can write that if delta Rg naught is equals to 0, then K equivalent is equals to 1, and we have appreciable conversion of reactants into products. Okay, and lastly, if we have delta Rg naught negative, then K equivalent would be greater than 1, and we have higher conversion of reactants into products. Okay, then let us see a concept wherein, let's say, on heating N2O4G, we get 2 moles of NO2G, and delta Rg naught for this reaction would be equals to 2 moles of molar free Gibbs free energy of NO2G minus Gm naught N2O4G. Okay, and delta Rg naught can also be written as delta RH naught minus T delta Rs naught. So let's say at 25 degrees Celsius, we can write that delta Rg naught is equals to 5.4 kilojoule per mole, or K equivalent is less than 1, and at 100 degrees Celsius we get that delta Rg naught is equals to minus 8.1 kilojoule per mole. So at this temperature, K equivalent would be greater than 1. Okay, so if we see the trend of Gm naught of 1 mole of N2O4, and mixture of NO2 and N2O4, so we can write that the Gm naught of 1 mole of N2O4 actually falls up to a certain limit, and then it rises here, which marks the Gm naught of 2 moles of NO2. Okay, so we would have some equilibrium point here. Okay, so this would be the trend So let's say this is point X. So at point X we can say that reaction is at equilibrium, okay, and delta Rg at temperature and pressure, at the given temperature and pressure, would be 0, or G of system at that temperature and pressure is minimum. Okay, and we can also analyze that equilibrium exists towards reactant side. So equilibrium exists towards reactant sides. Okay, and at 25 degrees Celsius, what we can say, that already we know that delta Rg is equals to delta Rg naught plus RT ln Q. So delta Rg naught would be positive, and at 100 degrees Celsius we can write that delta Rg would be equals to delta Rg naught plus RT ln Q. So in this case this would be negative. We already have seen the values, these were experimental values. So at 25 degrees Celsius K equivalent was very much lesser than 1 and delta Rg was positive 5.4, and at 100 degrees Celsius delta Rg naught was minus 8.1 joule kilojoule per mole, and K equivalent was greater than 1. So we can write that at 25 degrees Celsius, in both the cases we are talking about the equilibrium condition, so delta Rg naught would be 0 in both the cases. So in this case delta Rg naught would be positive, this would be negative, and in this case delta Rg naught would be negative and this would be positive. So we can guess how much a role delta Rg plays in defining the K equivalent of any reaction at a particular temperature. Okay, and one more reason that why equilibrium exists towards the reactant side is, we know that this is for Gm naught for pure NO2 and this is Gm naught for pure N2O4. Now N2O4 is converting itself into at equilibrium into NO2, so we get 2 moles of NO2 here. So already the Gm naught for NO2 is very much high here, so just to get at the equilibrium, and on the top of it also we are taking 2 times Gm naught of NO2 and we are subtracting it with Gm naught of N2O4, which was already lesser than Gm naught of NO2. So obviously the equilibrium would be towards the reactant side. So this explains why the equilibrium will be towards the reactant side. Okay, next, if we had, in place of the previous graph, if we had some graph like this or some states like this, in which we had for Gibbs energy of NO2, first let's see for N2O4. So for pure N2O4, let's say we had Gm naught here, okay, and for pure NO2, let's say we had Gm naught here for 2 moles. Okay, so before continuing that, let's first see more on this graph. So here this N2O4 is approaching towards equilibrium and it has to go till NO2, so it has to bring it down and as well as approach the equilibrium point. So in this case delta Rg naught was, or rather would be positive. Okay, because this 2 moles of Gm naught NO2 will be higher than Gm naught of N2O4. So this value would be, delta Rg naught would be positive. Whereas if we have this graph in which, let's say, initially Gm naught of N2O4 was higher, and the graph is something like this, where we have a equilibrium point at point y. So in this case 2 moles of Gm naught are lower than 1 mole of Gm naught of pure N2O4. So in this case delta Rg naught would be negative. Okay, so again I'm reiterating that we are taking N2O4G, heating it, and this is at equilibrium. 2 moles of NO2G are produced. So delta Rg naught would be written as 2 Gm naught NO2 minus Gm naught N2O4. Okay, so with this we come to the end of this lecture. In the next lecture we'll be seeing equilibrium constant from thermodynamics approach. So till then, good luck and goodbye.